Hi, my name is Jamie, and I'm going to be talking about how to use Pythagoras' theorem to derive trig identities. This video was originally created for MAT135 at the University of Toronto. Now, the goal is to derive some trig identities using Pythagoras' theorem, and if you're anything like me, remembering that sine squared plus cos squared equals 1 is easy, and remembering a lot of the other trig identities is quite difficult because we don't use them as much. So we know what to do if we see sine squared or cos squared. We know we can rewrite one in terms of the other, if that's a useful thing to do. But what happens if we have the square of a different trig function? So the example that we're going to look at in this video is rewriting sec squared in terms of other trig functions. And we're going to do that using Pythagoras' theorem. So we're not going to use the other trig identities that we already have. So first question, what's Pythagoras' theorem? That's our starting point here. So if we draw a right-angled triangle and we label the lengths of the sides, then Pythagoras told us that a squared plus b squared equals c squared. So that's the property that we're looking to use here. Now, what does that have to do with the trig functions? Well, we also have some nice properties of trig functions and how they relate to the sides and angles of right-angled triangles. So we're dealing with x here, so let's label one of these angles x. So what do we know about sec of x? Well, we know it's 1 over cosine, and that puts it in terms of a trig function that we actually have probably more accustomed to relating to right-angled triangles. So cosine, well, we know this is the adjacent side over the hypotenuse. So the adjacent side in this case is length A, and the hypotenuse has length C. So if we rewrite this, we find that sec is C over A. Now, we don't actually know what c and a are in this case, and we don't know what x is, but essentially these are both fractions. The right-hand side is c over a, that's a fraction. The left-hand side doesn't quite look like a fraction right now, but we can rewrite it as sec of x over 1, and then it is a fraction, and we can set a to be 1 and c to be sec of x. So a is going to be 1, c is sec of x. So this essentially defines the right-angled triangle. We've given the lengths of 2 of the sides. So the next question that we might ask is, what is b? If we know these are the values for a and c, what's the length of the third side? Well, we can either do that using sine or using tan. We've already used cosine to deal with the adjacent and the hypotenuse, and so if we want to work with the opposite side, then we need either sine or tan. You could use either here. The slightly simpler one to use is tan, just because the adjacent side, having length 1, is the simplest one we have currently. So we can take tan of x. We know this is equal to the length of the opposite side, which is b, over the adjacent side, which is a, which is the same as b over 1. So that means that b is tan of x. So we can fill that in on our triangle. And now we know what all 3 sides look like. How does that help us? Well, the original question was, what is sec squared? So Well, now we can actually use Pythagoras. We know the lengths of all three of the sides, and that's all we need to know in order to use Pythagoras' theorem. So sec squared of x, well, according to our triangle, this is the length c squared. And as we said before, Pythagoras tells us that c squared equals a squared plus b squared. And originally we didn't know what those lengths were, but now we do in relation to our original quantity, c, which was sec. So we've got a equals 1 squared, so a squared equals 1. And we have b equals tan, so b squared equals tan squared of x. So we've derived that sec squared of x equals 1 plus tan squared of x. And if you remember your trig identities better than I sometimes do, then you'll know that is one of the common trig identities that we come across. And so we've, instead of just remembering it or deriving it from other trig identities, we've actually calculated it from scratch using Pythagoras' theorem. And if you ever forget what the property is, then that's certainly an easy way to rederive it if you don't have the easy ability to look it up. So I'm going to leave you with an exercise, which is to use Pythagoras' theorem to rewrite cosec squared of x using other trig functions. So you can use a similar process to what we did here and derive one of the common trig identities from scratch using Pythagoras' theorem. Thank you.